Okay, so this problem is asking us to find K for this reaction, the equilibrium constant for this reaction, using thermodynamic data. And so in order to do that, the equation that links K to thermodynamics, one of the equations anyway, is this one, which is delta G, the standard delta G of reaction is equal to negative RT ln K. And this is asking for K, P, this is all in a gas state. Okay, so if I can figure out delta G, a standard delta G of reaction, then I should be able to use R and T to find K. And what I forgot to write in this problem was that I'm going to find this at 298 K. Okay, so you need a temperature to plug in there, so I've given you that. All right, so let's look at some thermodynamic data. So how do we find the standard free energy of reaction of this? Well, we do it using by taking advantage of the fact that delta G is a state function, so that all we need to do is add up the Gibbs free energy of formation of the products and subtract the Gibbs free energy of formation of the reactants. So if I look up those values, so delta G R equals, if I look up those values, well, let me just write this down really quickly. So this is going to be the delta G of formation at standard temperature and pressure, at standard temperatures for PCl3 plus the standard delta G of formation of Cl2 minus the Gibbs free energy, standard delta G of formation of PCl5. Okay, so all we need to do is look up the values for these, and we have these in many thermodynamics tables. Okay, so this equals, so the delta G of formation of PCl3 is negative 267.8 kilojoules per mole. Okay, and the delta G of formation of Cl2 is 0 because that's a standard state element, so that makes it easy. And then subtract the delta G of formation of PCl5 since it is a reactant and we're not forming it, we're actually breaking it apart. So we have to change the sign of it, and that's what we do by subtracting it. So PCl5 in the gas state, you have to be careful with the states that you're looking at because there's also information for the solid state on the one that I'm using. So minus negative 305.0 kilojoules per mole. Okay, if I plug all that in, 267.8 negative plus, because we're changing the sign of it, 305. That ends up giving us a standard reaction free energy of 37.2 kilojoules per mole. Okay, so what do I do with that information? Well, I'm going to plug it into this equation that I have up here. But before I do that, I'm going to do some algebra to isolate K. I'm going to do that symbolically. So first, I'm going to change the sign, and I'm going to switch my side that K is on. So I'm going to say RT ln K is equal to negative delta G of the reaction. So that's just an algebraic manipulation there. Then I'm going to divide both sides by RT. So I have ln K is equal to negative delta G over RT, pretty straightforward. And so how we isolate K is by putting all of the stuff on the other side of the equation as an exponent to e. So that means k equals e to the negative delta g r over RT. So now we can plug in our values, and we have this delta G that we came up with up here, so it's negative 37.2 times 10 to the third joules per mole. The reason that I changed that into joules is because I know that my R value has joules in it. So 8.31 joules per Kelvin mole. Okay, and then that's so because that's in joules, I have to put that in joules so they cancel each other out. And then my temperature is 298 K. Okay, so let us do this calculation here. It's 298. I'm going to get a number. It's a negative number, but so it's negative 15.02, but I'm going to take that as an exponent of E. So I'm going to do that in my calculator real quick. And what I get is 2.99 times 10 to the negative 7. Okay, and K doesn't have units. So we don't need to report units for K. So the second question is, are products or reactants favored? And I need to use my value of K to figure that out, but I can also use my delta G to figure that out too. So I have two pieces of information here, and they coincide. So first of all, my delta G is positive, meaning that this reaction as written here, up here, is spontaneous in the reverse direction, not the forward direction. And so I can use my positive delta G to say that reactants should be favored, but I should also use my K value to say the same thing. So this is very, very much less than 1, which means that when we look at the structure of this K, actually this is a Kp, so it's not concentrations, it's pressures. So the pressure of PCl3 times the pressure of Cl2, both of these are raised to the power of 1, since that's their stoichiometric coefficient. And then the pressure of PCl5 raised to the 1 is very much less than 1. So that means that this denominator is much larger than the numerator. Meaning that you have many more PCl5 molecules floating around in your flask than you do PCl3 and PCl3 and Cl2. And so from that logic, you can also say that this reaction favors the reactants. So pick an equilibrium reaction that has thermodynamic data in a thermodynamic table that you have access to, and just kind of practice this process of calculating the delta G of reaction, the standard delta G of reaction, and then using that to calculate K, and then kind of reason through, well then what then would my reaction flask look like if it was